Hello, thanks for listening in. It's great to have you with us. In this short video, we are going to develop a Lagrangian formulation for a classical electron that radiates its velocity fields at the speed of light. To do this, we begin with this animation here, showing an electron at rest, shining its Coulomb fields like radiating stars in the galaxy. Even though we violate conservation of energy here, at the same time we are all very familiar with 1 over r squared radiation fields. Let's suppose this electron moves at constant velocity relative to some arbitrary frame. Momentum flux fields follow simply by multiplying the conventional velocity fields E and B by a fundamental surface charge density, leading to new fields we will call pi sub E and pi sub B. And just like that, we have a brand new classical electron. Our stated goal is to build a Lagrangian density for this particle. To do this, we replace the Lorentz gauge condition with the vacuum gauge condition given by this formula. This leads to a set of radial potentials called vacuum gauge potentials. These potentials have two very important properties. First, they are null potentials, just right for describing a field that moves at the speed of light. And second, these new potentials have the very special property that they only determine the velocity portion of the field strength tensor, even if the particle accelerates. Now let's use vacuum gauge potentials to construct a vacuum Lagrangian. We do this by first writing a proportionality between vacuum gauge potentials and a 4-vector U nu having units of length. This new vector may be referred to as a vacuum dilatation vector. As it represents a distortion of a medium we will refer to as the vacuum. This distortion can be characterized by a vacuum strain tensor and a vacuum stress tensor as shown in this table. The stress tensor is equipped with a single constant modulus mu sub e, shown by the red arrow, which is exactly the outward pressure of the electron charge density, tending to explode the particle. Now we're ready to bring in the electromagnetic Lagrangian. We like this Lagrangian a lot, as everyone does, but we need to cast it into a different form to accommodate radiating fields. We do this by inserting the stress and strain tensors previously defined. This leads to a new Lagrangian composed of two free terms, but we notice that the second term does not lead to any equations of motion. It can be readily removed, and what remains is a very specialized vacuum Lagrangian well suited for a description of a classical electron radiating field energy or vacuum energy through its velocity fields. Now let's discuss a few interesting properties of this Lagrangian. First, it's important to mention that the point charge 4 current density has now become a point force density, which we call F nu sub E. Second, this Lagrangian has a structure very similar to and in analogy with the Lagrangian for the three-space theory of elastic media. In the four-space theory, the electron appears as a tiny microscopic orifice or excitation of a medium called the vacuum, which sits in the Minkowski space-time, just as a solid sits in a Galilean space-time. However, there is no undisturbed ground state in the four-space theory, as the stress tensor is equipped with an admissibility force constant, allowing the vacuum to create itself. Using the vacuum strain tensor as the field quantity, equations of motion for this Lagrangian determine the two inhomogeneous Maxwell-Lorentz equations for our momentum flux fields pi sub E and pi sub B. Of course, the homogeneous equations automatically follow from derivatives of the vacuum gauge potentials, and this completes our reformulation of the Maxwell-Lorentz equations in terms of momentum flux velocity fields. Next, consider calculating the stress tensor from this Lagrangian. Before we do this, we need to account for additional stresses due to the flow of the vacuum field. We do this by adding a term to the stress tensor proportional to the metric and inserting it into the vacuum Lagrangian. This new Lagrangian, even with the additional term, does not alter the equations of motion. Meanwhile, the total stress tensor T mu nu generated by the two-term Lagrangian also has two terms. The first term in brackets is identical to the symmetric stress tensor of the electromagnetic theory and must be symmetrized in a similar way. In addition, there's now a new term contributing radiation stresses shown by the floating red arrow. Particle accelerations have not been discussed yet, but this is easy to do by adding a term to the vacuum strain tensor. Next, define a tensor R mu nu out of the generalized strain and include a relabel of the propagation term as lambda mu nu. This produces a set of equations complete with a cosmological term and having a very Einsteinian appeal. Again, terms in brackets are exactly the symmetric stress tensor of the electromagnetic theory, while the radiation term stabilizes the particle and generates the outgoing flux of vacuum energy. In summary, we've used the electromagnetic Lagrangian to develop a very powerful theory of potentials, well suited for a description of the classical electron with radiating velocity fields. Unfortunately, we've also left a lot of basic questions unanswered. For example, does a radiating Coulomb field exert a force and can it be quantized? Also, is the motion of the Coulomb field detectable? These are all great questions that can be answered in another video. For now, thanks again for listening in and have a great day.